Uber moves 25 million riders a day across 70 countries. It picks your driver in under 500 milliseconds. But here's the twist. It almost never picks the nearest one. Think of it like an air traffic control tower, deciding which plane lands first, not which one is closest to the runway. Picture Uber's first naive version. Always match the nearest driver. Sounds perfect. But the nearest driver might be heading away from you. A driver 3 blocks further could arrive 2 minutes sooner. In a control tower, closest runway isn't always the fastest safe landing. There's a deeper trap. If every rider grabs the closest driver, popular zones drain first. Drivers pile into busy areas, fringe neighborhoods go empty. Local optimization creates global chaos, exactly what air traffic control avoids by managing the whole airspace, not one runway at a time. Uber felt this pain by 2016. Their simple proximity lookup left drivers idle and riders waiting, so they rebuilt matching from scratch using forecasting. Result: driver utilization jumped 30%. That's the moment Uber's dispatch stopped acting like a taxi stand and started acting like a control tower. Here's what nobody tells you. Making riders wait longer actually makes rides faster. Uber holds your request for 3 to 5 seconds, batching it with everyone nearby. That tiny delay lets the system see the whole board, like a control tower holding planes briefly to sequence a faster landing order. So how does Uber see the whole board in milliseconds? Enter H3, Uber's hexagonal grid covering the entire planet. Each hexagon is a radar sector, roughly 0.1 square kilometers. Drivers ping every 4 seconds and slot into a hex. It's the control tower's radar, one glance, every plane, every sector. Why hexagons, not squares? Squares distort distance. Corners sit farther than edges. Every neighbor of a hexagon is the same distance away. For a control tower tracking planes, uniform sectors mean no blind spots and no distorted math. That single design choice makes radius searches faster and fair. Every active driver sends a location ping every 4 seconds. Multiply that across a global fleet and you get over 1 million pings every single minute. That's a fire hose of GPS data hitting Uber's servers non-stop, and it all has to land somewhere fast enough to matter. Uber built a custom location service to catch that fire hose. Pings flow into Apache Kafka, a real-time data stream, then land in a distributed, Redis-like in-memory store. That store is the radar screen every dispatch decision reads from. Always current, never stale. When you request a ride, the system doesn't scan the whole city. It starts at your hex, searching a 1.5 kilometers ring outward. Ring 1 checks 7 hexes. No drivers? Expand to ring 2, then 3. A control tower widening its radar sweep only until it spots enough planes. Not every nearby driver counts. The system filters out wrong vehicle types, drivers mid-trip, accounts flagged for too many back-to-back rides, and suspended profiles. Only clean, eligible planes stay on the radar before the tower even thinks about sequencing a landing. Each remaining driver gets a score, not just distance, ETA, rating, even how leaving their zone affects future supply. Here's a simplified version, using H3's built-in grid distance function to approximate arrival time before real routing even happens. Instead of matching you instantly, Uber holds your request in a queue. For 3 to 5 seconds, it collects every pending rider and every available driver nearby, building the full picture before making a single assignment. Under the hood, this becomes a graph problem. Riders on one side, drivers on the other, edges weighted by score. Uber runs the Hungarian algorithm, or a fast approximation, to find the assignment that's best for everyone, not just the loudest request. The payoff? Batched, globally optimized matching beats greedy nearest driver matching by roughly 15%. Multiply that across 25 million daily rides, and you get millions of minutes saved. Riders waiting less, drivers driving less empty. Every rider sees an ETA before accepting. That number comes from a deep learning model on Uber's ML platform, Michelangelo. It ingests the road graph, live GPS traffic, time of day, and historical speeds, then predicts arrival in under 100 milliseconds. That single model handles a staggering load. 1 million ETA predictions every second, globally, each returned in under 100 milliseconds. It's the control tower's flight time calculator, running continuously for every plane in every sector, all at once. Uber doesn't just react, it forecasts. Every 5 minutes, models predict rider demand and driver supply for every hexagon. That prediction powers 2 things: surge pricing when demand outpaces supply, and proactive nudges asking drivers to reposition before the shortage hits. Think of surge pricing like a control tower rerouting extra planes toward an overloaded runway. Price signals pull more drivers into hexagons that need them most, rebalancing the whole map before riders even notice the imbalance forming. Once matched, your trip becomes a state machine. Requested, matching, accepted, driver en route, arrived, in-trip, completed. Every transition is stored in Uber's schemaless database, triggering push notifications, payment holds, and fresh ETA updates downstream. Zoom out, and the entire flow looks like this. Rider requests, system finds candidates, batches and scores them, dispatches an offer, and the driver has 15 seconds to accept, or the offer moves instantly to the next best candidate. This isn't theoretical. Uber runs this across 10 global data centers, each handling its own region with cross-region failover. Peak load, 250,000 concurrent driver location streams, with every batch decision finalized in under 500 milliseconds. Uber open-sourced H3 in 2018. Lyft runs a similar playbook, batched matching, bipartite scoring, but swaps Uber's XGBoost model for a neural network, optimizing for driver earnings per hour instead of pure speed. Different priority, same control tower logic, processing 1.5 million rides a day. DoorDash took the same architecture and made it harder. A dasher can carry multiple orders at once, turning matching into a vehicle routing problem, NP hard, meaning no perfect solution exists in time. Their fix, approximation algorithms with a strict 200 millisecond budget. If an interviewer asks you to design this, the trap is matching greedily. Nearest driver, instant assignment. That's the wrong answer. The senior answer batches requests, indexes geospatially, and forecasts supply. That's the difference between a taxi stand and a control tower. In your next system design interview, say exactly this. I'd use hexagonal geospatial indexing for candidate lookup, batch requests for a few seconds to solve a bipartite assignment problem, and layer in demand forecasting for surge and repositioning. That sentence signals you've thought like Uber's engineers. Uber's matching engine isn't a taxi stand grabbing whoever's closest. It's a control tower, batching requests, scanning hex-shaped radar, forecasting weather before it hits. Next time your app makes you wait 3 seconds, that's the tower sequencing your landing. Subscribe for more system design breakdowns.